Welcome to Coding for LARP, Lessons Learned from Odysseus. Let's get started. My name is Sampo Juustila. I've been coding for over 30 years, half of which has been professionally coding. I was one of the core developers for Odysseus for both the 2019 and 2024 runs. And my focus area was engineering views, engineering tasks, and the back end, but I dabbled with pretty much everything in the system. So, the point here is to go through a bit about what are the special requirements when coding for LARP, how to get the most bang out of the time spent, and some maybe pitfalls that may come up. This is maybe focused on larger scale LARPs like Odysseus, but hopefully there's also useful pieces for smaller productions. A bit about Odysseus. I believe most of you know it. A large-scale sci-fi LARP held. There were 3 runs, a total of 312 players, over 25 countries players came from for the 2024 run. Over 200 volunteers were organizing it, almost 200,000 euro budget. I checked that there was 48,000 lines of code written for Odysseus 2025. The number for 2019 was around 33,000, so 18,000 more for last year's run. And that's not including 8,000 lines of like data initialization there. And around 6 kilometers of cable laid within that single school. That's a number from 19, so we think we went past that this time. Here's a few photos about the tech, just to give a feel of the atmosphere. So there were a huge amount of integration points. There were specialized screens for engineers, for bridge, screens used by all players to send messages and so on. There were physical tasks which were integrated within the back end and so on. So we'll dig into those a bit more. And it was also the lighting and sound were extremely immersive. Pretty much all of the lights on the ship were controllable, and the lighting changed based on what work shift was going on. And in yellow and red alerts, it would change. And a very immersive soundscape, and a full 50-hour clockwork LARP, with each character having their own plots with other players and NPCs. But digging into the more technical side, on architecture and NFRs, so non-functional requirements, this is the basic architecture we had in Odysseus. This is from 19. The sound and light side changed a bit for last year's run, but the tech side was pretty much identical. So there's the main backend server, which we coded. Then we had empty epsilon, which was used for the bridge simulation. There were empty epsilon devices on the bridge, and then the fighters and the empty epsilon and backend were synced. And then there were numerous different endpoints which were integrated with the backends. And basically the architecture here was that everything communicated with the backend server, with the exception of the empty epsilon server, which handled the empty epsilon clients. And then the empty epsilon server and the backend server were synced. Basically, the backend server was the master for all data. So that's the place where everything is stored, with the exception of the empty epsilon ship health, which was in the empty epsilon server and synced from there. And even there, it was during jumps, it was cut off, and the empty epsilon scenarios were reset during the jumps. So during that time, the ship health was stored in the backend server. So when we started in 2018 discussing these, actually I think it was 2017, we went through some non-functional requirements, like security. Who needs it? We had a full intranet where we trusted all clients that are on that intranet, and we trusted all users of the clients on that intranet. So we just decided we don't need security. All clients had full read-write access to all data, which made a lot of things very easy. Including the public endpoint that the players used had a hacking mode, and the hacking mode is pretty easy to implement when you can just change the user ID that's being sent to the backend server. So it makes a lot of things very much easier than in professional settings. Maintainability. Rarely an issue, especially for one-shots. So that means that manual testing is often sufficient. We mainly made automated tests for the very core functionalities, but otherwise we're relying a lot on manual testing, while in professional scenarios, when you're expecting it to be developed for 3 years or 5 years or 10 years, you want to pretty much automate test everything. The one thing we noticed for the 2024 run was that there is quite a bit of bit rot over the years, meaning that, for example, the Node.js had several major releases. Many of the libraries weren't compatible or had been deprecated. So there was quite a bit of work to upgrade from the 2019 to 2024 run just to make the same software work again. But in many scenarios, that if it's a one-shot, it's not that big of a deal. And scalability, 100 users is enough. In most cases, the data you have also is quite limited, like hundreds of items or thousands of items, which means that you can move all of the data from the server to the client and do a lot of stuff on the client side, like filtering and so on the client side. While if you have like 10,000 or 100,000 pieces of data, then you would need server-side filtering, so you wouldn't need to move all of that data, for example, to a phone or a Raspberry Pi device. So here the maybe points are to embrace quick hacks, but keep the core clean. So quick hacks were done a lot in many places, but the very core, I think, was very clean and very modular and efficient, and I'll come a bit back to that. And especially in this kind of larger LARP, we focused on the framework to help implement the functionality, and once the framework was there, a lot of the functionality was very easy to implement. On the infrastructure side, I wasn't that much doing stuff with this, but wired versus wireless communication is mainly the question of reliable versus convenient. And there we decided the most important connections, especially between the backend and empty epsilon server and the empty epsilon server and the empty epsilon clients, which had to work all the time, those were pulled with wire. But otherwise, for the communication of the laptops and the engineering tasks and so on, we used wireless network purely for the sake of convenience. And we didn't have a lot of, or I'm not sure did we have any issues there. The light and sound used purely wired because, well, they're professionals and they're used to doing stage stuff where there's hundreds of or thousands of mobile phones causing interference, and also the controllable lighting can cause interference and so on. So also the lighting used on purely wired communication. But that said, we didn't have pretty much any problems with using wireless. Of course, it needs to be set up there as well. Then the question of build time versus runtime requirements. Set up the infra early on. In 2019, we got the intranetwork running, I think, 1 day before players came on site, which meant that we had pretty much no time to test anything there. There were a lot of troubles getting the network set up and running, and it was hell, and I'm very amazed that everything worked so smoothly despite that. Another thing we noticed this time was that, well, relating to the external connectivity, I recommend you have it. We initially, for 19, were considering a purely intranetwork without any external connections for security reasons. But just maintaining the systems, it's so much easier when you have external connectivity. You can do Git pull for the devices, you can do updates, you can do installations, and so on. So have an external network there, remembering NAT firewall in between. For the later run, we also had a VPN connection so that maintainers could, from the internet, connect inside the intranet. And this was for the 2024 run because at that point, several of the maintainers weren't going to be on site all of the time, so they could connect in and do fixes. It was used somewhat, so again, depending on whether the core people are going to be on site or not, consider whether it's worth the setup effort. It wasn't, I don't remember what the VPN was, but it was free for this kind of small scale production, so it wasn't a big setup. But related to the external connectivity, one issue was that it was set up early on. Many of the build team who were setting up stuff were connecting their devices to the network. And then when we're getting closer to the actual run, we noticed that the external connection was quite saturated, because just having devices connected to the Wi-Fi means that the devices are using it to download images, download software updates, and so on. So if I'd be doing this again, what I'd do would be to set up two Wi-Fi networks, both initially, one for build time and one for runtime, and then the build time, everyone connects to the build time Wi-Fi, which is then torn down before the runs start, so we can clean up all of the extra clients. Yep. Question was on the operating system. Both Windows and Linux were used in the setups. I think that Empty Epsilon was running on Windows and everything else on Linux. I'm not 100% sure about that, but that's what I'd recall. And then, of course, build and maintenance crew had whatever they have. Automating startup, that's a good idea, especially if you don't have the DevOps maintenance on site all the time, and like pretty much everyone there. And that's useful if you have a power outage or any other failure during the run, so it's easy to get back up and running. In 2024, the failure was me, because I was one of the engineering tasks was broken, and it was Raspberry Pi based. I had an SSH connection there. I was debugging it, and for some reason I couldn't SSH directly to it, but I needed to SSH to the backend server and from there to the Raspberry Pi. And then I rebooted it from the command line and then realized I was on the backend server. I ran into the GM room, shouted that emergency. I just rebooted the backend server. Laura, the main coordinator there, the first thing she said, okay, calm down everyone, let's sort this out. And we were just in the middle of a jump, so all of the systems on the player's side were down. And we called Nico, who had set up all of this stuff, and he was like, well, it should just start up automatically. And after a few minutes, the backend server had started up, fetched everything from the database, everything was running smoothly, and the players probably didn't notice anything other than a slightly longer jump than usual.
Which run was this in 2024?
It was the first or third run. I think yeah.
It might have been the third one, because I was thinking we had a jump that was extra long. So that's why.
Yeah, I think it was the third one. And last point, keep it simple. We were considering having like separate intra-networks for like all of the tasks and such, and a separate one for audio and video streaming. But ultimately we scrapped that for simplicity. A single network that's fast enough, and then just try to get the external connectivity also to be fast enough. Then to the interesting part. So this is basically the core logic of most of the functionality for Odysseus. And I came up with this pretty early on for the 2019 run, and I'd say that this is maybe one of the reasons why the tech side of Odysseus was so successful. There's a simple in-memory database which contains generic data blobs, which are just JSON objects. Sorry, this is a bit technical presentation, so bear with me. It's basically just storing any sort of data in the in-memory database. Then there is a generic API. We had HTTP REST API for, like, you could fetch the data and you could update the data. And then we also had WebSocket, in our case, socket.io based API, by which any changes that occur on the server are sent immediately also to the clients. So the data updates on the clients immediately. And on the client side, we had admin UIs, we had player clients, laptops, we had physical puzzles, which were Raspberry Pi based or ESP32 based, and we had mobile phones, the Hanska device, which was Android. Oops. And using this kind of generic data store with a single API reduced a huge amount of, like, boilerplate code. Before that, there had been, like, for the ship fleet, we had a separate API. For the NPCs, we had a separate API. For the empty epsilon health, we'd need a separate API. All of this boilerplate. When we just dump it into the generic data store, we have a single API that's ready, and all clients can just read-write it immediately with a single framework code. Then we had integrations, mainly the empty epsilon server. There again, it was the empty epsilon didn't support pushing state to the backend, so it was once per second asking for the empty epsilon health from there, and it was updated into the in-memory database. And then there was a separate rules engine in quotes. All of this was something like a few hundred lines of code. And the rules were separated from everything else. So basically, just when the data changes, there's simple rules that see that, hey, this changed, let's do this and this. And then there was a data persistence, so the data itself was stored in memory, and it was just stored onto the disk, so that if the server crashes or someone restarts it, you can read it back in. Any questions before I dive into examples?
Were player clients completely anonymous, or did you have to do some sort of account setup before the game started?
Well, the players had, like, accounts with which they could sign in. So, and that was also like their name tag had an ID on the other side, and you just logged in with that. So very simple system. And also for the security, we did have, during development time, we had a server running in public cloud, which you could access. And there we had set up, like, simple HTTP basic authentication. So it's not publicly accessible, but even that was disabled during the actual runs. So going through a couple of examples on what this means in practice, an example of the data blob structure. There was a type and an ID, which together was a unique identifier for that data object. And this was also very useful because, for example, the engineering tasks had a type task, and then the physical puzzle, like the fuse box, had a separate object which had type box. And both had the ID fusebox bridge. So you could easily like map these together because they're separate type and ID. There were a couple of timestamps created at and updated at, which were updated by the server when you create it or update them. That's very useful for like admin monitoring. How often has this been updated? Is this up to date? Has some task crashed and it's no longer updating this? There's a version number which is updated by the server for optimistic locking. Optimistic locking means that when you fetch a data object and you have like version 5, then you want to update it, you send the server that I'm updating version 5 with this data. And if the server still has version 5, then it updates it. But if the server has version 6, then it means that someone else has updated it already and it rejects the update, and then the client fetches it again. So you don't get conflicting updates. And then everything else in this JSON object is just free fields which are for that particular object. It can be engineering task configuration or game configuration or empty epsilon health or so on. An example on the rules. You just have a watch function. You're watching data of type ship and ID EE, which contains the empty epsilon health. You loop through the empty epsilon health types. You fetch the previous health and current health, which is just getting values, but there were some exceptions. And if the current health is lower than the health it was previously, then you break tasks so that it corresponds. And you just have a lot of these separate rules which are based on those small pieces of data. And that separates the logic a lot, so you can easily create these tasks. I'm running a bit late, so I'm hurrying forward. An example. There was an engineering task where you had to physically kick a device in order to fix it. There was a metal plate there. It breaks randomly about once per hour. It shows up in the engineering tasks. There's a plasma ball behind that. When it breaks, it turns off. And when you kick it, it immediately turns on. There's an electric buzzing noise when it's broken. And there's this big battery that you need to recharge on every jump. And if this is broken, it doesn't charge it fully. It only partially charges it. Any guesses how much time or how much code this took?
50 lines, maybe?
Close, a bit more. I'll go through all of it here. So bear with me if you're not a coder. This was something I was planning for 2019, but didn't have time to set up. And on Midsummer Eve at midnight, I remembered it and put it into our Discord. That, I was thinking, but well, of course, I no longer have time for this. Half an hour later, at midnight, this was the stage. So that's when it became the thermic fusion regulators. So that escalated. The implementation, there's a metal plate, there's a ball that is hung by a wire there. And there's a Raspberry Pi that just measures whether the plate and the weight makes contact together. When you kick it, it breaks the contact for a moment. There's logic for breaking the task about once per hour. There's logic for the battery charging. There's a DMX signal sent for light and audio when it's broken and when it's fixed. And there's power plug configuration. And the electric buzz sound is on the sound side. Here's the task definitions. There's the box, which is the physical device. You'll get these slides at the end of the show, so you can see everything there. So there's, I also added this like kick probability, so necessarily the first kick doesn't fix it yet. But I guess it was kept at 1 all the time, so the first kick fixes it. And there's a configuration that which Raspberry Pi pin it's using for measuring it. And then on the engineering task side, these are tied together, the task and the box. There's a failure per minute probability, so a 1% chance of breaking every minute. And then what the battery charge level is if this is broken. And then 2 DMX signals to be fired when this task is broken or fixed, and then engineering task views. This is pretty much the implementation on the Raspberry Pi side. There's a bit of initialization here. This init pin is something like 10, 15 lines of code. And then this callback tally measures whether the contact has been lost or regained. So if it's greater than 0, it means the device has been kicked. And if the status isn't fixed, then it fixes it. And that's it. This is for breaking the task. We're just once per minute running this function, which gets the task, gets the probability, checks the jump state. There's some conditions on when it can become broken, and if it occurs and it's not broken, then it breaks it. For the battery charging, these highlighted lines were the ones changed. So instead of just always charging it to 100%, we fetch the task, and if this task is broken, then we take from there this configuration battery charge level when broken. Otherwise, we charge it to 100%. 3 lines of code. And controlling the plasma ball, that was again something in the framework code. So when a DMX signal was triggered, this was actually server code that tied into this DMX signals. So it's like generic signal which is sent also to DMX, but it can also be used for other things like controlling TP-Link power plugs. And there's the IPs, and it sets the power state to false when it's broken, and true when it's fixed. And then the plasma ball is just plugged through that. And I counted that this was in total 110 lines of code for implementing all of this functionality, which is pretty insane, I'd say, for the functionality. And it shows the power of having this decoupled framework code and then building on top of that. And another example there was that the second run, in their Discord, they had invented an NPC cat on board. And the team had heard about it and gone wild. There was a cat sleeping box and different signs that cat is not a certified gunner. And there was a cat bowl where cat food was added and it disappeared occasionally and stuff like that. And I was playing in the second run. I was completely immersed there. And the people on in the GM room were feeling bored. So during the game, they added, there was this DMX signal that when you kick it, it fixes it. And they added that there's a 1 in 4 chance that when you kick it, there in the engine room, it sounds a cat screeching and scuttling off, resulting in this. So yeah, if there's something to remember from this, it's this. Generic data storage, generic APIs, and then a decoupled rules engine that's just modifying the data. And all of this framework code is like a few hundred lines of code. Moving forward, a bit on the clients. So there were a lot of different clients and endpoints. So there were laptops, mainly borrowed from B2. So they're free. They're the same ones used here in the cons and can be used for these kinds of activities. The data hub was like for all players, for communicating with each others, for communicating with the GMs, and communicating with NPCs. All built with web technologies. The engineering view, this was built based on NASA OpenMCT, which NASA uses for their own mission operations data visualization. And that just was, I just took it and hacked away like so that the dates are shown correctly and so on, and it gave like an extra feel of refinedness there. Phones are useful. Odysseus had this hand scanner built also using web technologies. Web technologies can use a lot of the phone sensors nowadays. We used NFC a lot, so engineers had the hand scan and you scanned an NFC tag somewhere and you got a puzzle, mini puzzle that you had to solve in order to fix that engineering task. You can access GPS, go full screen, the accelerometer, and so on. One point to note here is that if you're doing this using web technologies, which I recommend, many of these advanced functionalities are limited to websites that have valid SSL certificates, which is a bit of a pain when you're on an intranet network. And we had a lot of pain with that in the 2019. In 2024, we bought a domain and generated a valid SSL certificate for that external domain and made that just the IP point to the internal IPs. So that way, we easily got the valid SSL certificate for it. In 2019, we tried managing without an SSL certificate, and it was painful. We had TV info screens, Android tablets. So we had a couple of airlocks where you had a tablet view there, which you used in order to get in. And then there were physical devices. We had framework code for Raspberry Pi, allowing very easy implementation of engineering tasks. The example of the Kickbox was one of those. A Raspberry Pi for just detecting a contact loss is very overkill, but they cost like 20 euros a piece. We had extras lying around, and it's just bloody fast to implement. ESP32 is completely fine. This is the big battery I mentioned. It was built, I forget the name, but the props were built. I built the tech there. There was a LED view there. The cable lit up. There were animations on the cable, it flashing when you connect it. There were animations on the power bar when the ship is jumping, and so on. And all of that was around 750 lines of code, a lot of which were these animations. And there were like fuse boxes which physically blew fuses which the engineers needed to change, and a huge button board with buttons and so on. So, and really awesome alien artifacts made by Armin Sass. So, and most of this was built using web technologies, so I recommend that. Now I'm running really late. I have, I guess, 5 minutes remaining. Yeah. Even though you can integrate pretty much everything, not everything needs to be integrated. There were a lot of manual tasks which just had instructions. You need to open this, you need to do this and this, you need to put it back together, and then you just tap in the Hanska that now I've completed this, and you trust the players that they've actually done it. So this gives a lot of variety to the work the engineers need. Quickly skimming through admin functionalities, we had a full admin view with access to the data stores. You could edit the data stores there. There was a separate view for the jump drive, and all of these buttons and actions, they're actually just changing a few values in the data store. So it's changing the, for example, what the state of the jump drive is. Documentation is important. There's a flow chart of the jump cycle with the dotted lines, like going exception routes, that if they're jumping to the wrong location, then the GMs prevent that, and so on. Empty epsilon connectivity. Really useful one was like being able to manually fire DMX events. You could do it from the light desk, but that needs someone who knows how to operate the light desk. Anyone can use this. And for 2024, they built a completely separate like admin story tool, which contained like all of the characters, all of the information, the plots these are connected to, and the events these characters are involved in. And there were even like these pre-written messages, because in 2019 all of these messages had to be written at the time and remembered to be written and sent. So this took a lot of pressure from the handful of people who knew this through and through. So you can just send them with a single click from here. LARP Manager is a tool which was released to open source a couple of months ago. And this promises a lot, like character management, LARP sign-up and payment processing and accounting, event setup, a casting algorithm, email sending, and so on. And this is free to use. So if you're doing something, I'd take a look at this. I haven't used this for anything, but worth a mention. This wasn't available for Odysseus, so we haven't taken a look at this. Light and sound integration. In 2019, we held a full presentation of this. It's available online, so there's a lot more talk and details there. The very, very short version is to use DMX. DMX is a standard protocol for controlling stage lighting and effects. On the physical layer, it uses RS-485, or you can also nowadays run it over Ethernet using converters. The basic idea is that you're all the time sending this frame of 512 channels over the wire, each of which can have a value. So you can, and that value controls, for example, a light brightness. And there can be different sources. In our case, we had a USB adapter on the back end, so the back end could send them, and then the empty epsilon server was also sending those. So that avoided any delays when the ship is hit and the displays on the bridge flash, then the boom sounds immediately. So thinking a bit about that as well. But there's a presentation online that you can check out. Any remaining questions? There's the link to this slide set. There's the link to the the previous presentation, and then the all Odysseus source code is available as open source. Any final questions?
Was there any misuse of the interface or systems, or did the players accidentally broke anything during the game?
I'm not aware that they broke anything other than some of the physical stuff that they were meant to use and handle. But like for the digital interfaces, I'm unaware of any such misuse or accidents. And in 2019, I guess once empty epsilon crashed. But when we were testing it originally, it crashed something like every 15 minutes, so it was a lot better than that. If there's nothing else, thank you for this, and I can stay here for a moment and answer more questions. Was there still a question?
What was the most fun to code?
Well, a lot of them. I was really into the engineering tasks, but I mean the kickbox was really fun to get implemented, and it was done I used maybe a couple of hours in the physical building, a couple of hours in coding, and a couple of hours in testing. And that's it. It was implemented like one day before players arrived. So you can, and stuff was also added between the two runs. So it was fun. Thank you.